In this video, I'm going to go through the review for the similar triangles unit. So starting with number 1, part A. Each of these say for each of the following, determine if the two triangles are similar. If so, by which similarity criteria? And remember, we could prove that two angles are the same, and I call that angle. Or we could prove that all three sides are in proportion. Or we could show that two pairs of sides are in proportion, and the angle between them is congruent. So let's just take a look at A. It looks like they give me all the side lengths. They give me this 60 right here, a 20 right there, and a 120 and a 30. So the first thing I might start to do is I'm going to check these proportions to see if my side lengths are proportional. So if I take 60 and divide it by the corresponding side, which would be 20, I want to see if that's equal to when I take 120 and divide it by the corresponding side, it's 30. So what I could do here is I can cross multiply to see if this proportion is true. So I can do 60 times 30 to get 180. And I can do 20 times 120 to get 240. Now notice that these aren't equal. So because the sides aren't in proportion, I can't say that these triangles are similar. And you could check that for the other ones as well, and you'll find that, yeah, 108 over 36 is equal to 60 over 20, but I need all three pairs of sides to be proportional for these triangles to be similar. So for B, notice I'm only given two pairs of sides. I have a triangle right here, triangle HDX, with side lengths 20 and 30, and I've got the bigger triangle, triangle HQN, with side lengths 60 and 40. Now notice that both of these triangles share angle H. So angle H is congruent to angle H by the reflexive property. Let me just check the proportions of the sides. It looks like HD should correspond to HQ, and that HX should correspond to HN. So I'm going to set up a proportion. I'll start with small with the corresponding big side equals small over the corresponding big side. Alright, to check to see if this proportion is true, I can cross multiply again. 20 times 60 is 120, and 30 times 40 is 120 again. So these triangles are similar because two pairs of sides are in proportion, and the angle between them is congruent. So by the side angle side similarity criteria, I can say triangle NHQ is similar to triangle XHD. Now be careful with the order of the letters there. Notice that X is the first letter there, and N is the first letter there. The reason I do that is because N and X are my corresponding vertices. You could see that in the picture as well. And I know H should correspond to H because that angle is the same, and Q should correspond to D as well. So just be careful about the order of the letters there. Now C is a little bit easier for us because there's actually no work we need to do. They've marked that angle C is the same as angle N, and I also recognize that I've got these congruent vertical angles for angle DSN and angle CSP. So by angle, these two triangles have to be similar. So triangle NSD is similar to triangle CSP. Again, just be careful about the order of the letters there. And for D, this should have a 4 and this should have a 6 there. And I think that should be 8. So again, I notice I've got a congruent angle right there and right there. And I'm going to check the proportion of the sides. If you're not sure which sides match up with which, picture if I rotate this triangle. If I rotate AE all the way around, it will coincide with EC. So I know that AE and EC are my corresponding sides, and BE and ED are my corresponding sides. And again, I'm going to do small over big equals small over big. I could already see in my head that both of those reduced to 1/2, so this is looking pretty good. And when I cross multiply, 4 times 12 is 48, and 6 times 8 is 48. So this is another side angle side proof, where two pairs of sides are proportional, and the angle included between them is congruent, making triangle CDE similar to triangle ABE. For number 2, triangles ABC and DEF are drawn below. If AB equals 9, BC equals 15, DE equals 6, and EF equals 10, and angle B and angle E are congruent, which statement is true? Well, this looks like it could be a side angle side justification for these triangles being similar. So let me give that a shot. I want to see if when I compare AB to the shorter side there, so I'll compare the shorter side to the shorter side, and I'll compare the longer side to the longer side to see if those sides are in fact proportional. Well, let's find out, right? 9 over 6, I want to see if that's equal to 15 over 10. So you could check this out in your calculator. 9 times 10 is 90, and 6 times 15 is also 90. So I think this is a pretty good justification for why these two triangles are in fact similar. Let me go through these answer choices though. Angle CAB is congruent to angle DEF. Well, that one right there, that can't be true because I already know that angle B and angle E are the same. So those would not be corresponding angles. For answer choice 2, AB over CB is equal to FE over DE. Well, that's saying two big sides over is equal to two small sides divided. And that starts with the smaller side over the bigger side. So let me just check that proportion, right? 9 over 15, is that equal to 10 over 6? Well, 9 times 6 is, what is that, 54? And 15 times 10 is 150, so there's no way that's true. And I've already proven these triangles are similar. I just need to check the order of the letters. Triangle A, B, C. Let's see, AB should match up with ED, so AB and DE, that's okay. And BC should match up with EF. Okay, BC and EF. The order of the letters is okay. Let me just check answer choice 4. AB, which is 9, over DE, which is 6, is that equal to FE, which is 10, over CB, which is 15? Well, I could already see that's not going to be true because 6 times 10 is 60, but 9 times 15 is going to be 135. So that proportion is not true either. So really, you've just proven that these two triangles are similar by the side angle side criterion. For number 3, in the following diagram, if AC is 12, DE is 8, and EC is 4, find the length of BE. So I'll label BE as X. Now, when my triangles are overlapping, I often find it easier for me to separate the triangles, for me to be able to visually process what's going on. So D, B, E, and I'll draw a bigger triangle for triangle ABC. Now I'm going to assume these triangles are similar. I know that DE is 8, BE is X, AC is 12, but BC, if I try to label that whole side, part of it's X and the other part is 4. So if I wanted to find the whole side length, I could label that as X plus 4. So if I'm setting up a proportion here, if I start with DE and AC, those are corresponding sides, and BE and BC are corresponding sides. So I could do DE, which is 8, over AC, which is 12, equals X, which is BE, over X plus 4, which is BC. So I'm going to cross multiply from here. Just be very careful. One of my diagonals multiplies to 12x, right? Because x times 12 is 12x. but I'm multiplying my 8 to two different terms. I'm multiplying it to an x, and I'm multiplying it to a 4. So make sure you remember to distribute into the parentheses there. This becomes 8x plus 32 is equal to 12x. I'm going to subtract 8x on both sides to get all my x terms together, because 8x minus 8x is 0. And I get 4x equals 32, or if I divide out the 4, I get that x is equal to 8. And remember, I labeled x for BE, and that's exactly what I'm looking for. So my missing side length is 8. So this is another proportion problem. You just need to be a little bit careful when you're distributing there. That's the only difference. For number 4, in the accompanying diagram, CA is parallel to XY, and CY and AX intersect at T. Prove triangle CAT is similar to triangle YXT. I'm going to make my statement reason chart, and the only relevant thing I see in my givens is that segment CA is parallel to segment YX. And I know that because it's given. Now my goal for proving the two triangles are similar is that for a Euclidean proof, I really, for the most part, want to show that I have two pairs of congruent angles. And there's a lot going on here. I want to think about why they told me that those segments were parallel. Usually I'm either looking for congruent alternate interior angles or congruent corresponding angles. And if I look along this transversal right here, it looks like angle A and angle X are going to be congruent alternate interior angles because they formed the Z there. So I'm going to say angle A is congruent to angle X. My reason being is that parallel lines form congruent alternate interior angles. Now you would write all this out. I'm using some shorthand here just to save some time. You might also notice that angle C and angle Y are another pair of congruent alternate interior angles if I look along the other transversal. You can do that if you see that, or if you want, you could also notice that, hey, those are congruent vertical angles there. So I could mention that that angle on top, angle CAT, is congruent to the angle on the bottom, angle XTY, because vertical angles are congruent. You don't have to do this. You could also use the other pair of alternate interior angles and just lump that below step 2 there. Now I've proved I have two pairs of congruent corresponding angles. That's enough to say triangle CAT is similar to triangle YXT by angle. For number 5, triangle ABC and DEF are shown below. If AC equals 8, AB equals 12, BC equals 6, DF equals 10, DE equals 15, and EF equals 9, state whether or not the two triangles are similar. Well, I'm given all three side lengths, so I'm going to check to see if all three sides are in proportion. So let me check this out here. It looks like side AB should correspond to DE, so AB, I'll highlight that in blue, should correspond to DE. If I'm looking at the order of my letters again, BC should correspond to EF, BC should correspond to EF, and just by process of elimination, it looks like AC should correspond to FD. So let me set up a proportion there. If I compare 15 over 12, I want to see if that's the same thing as if I compare 9 over 6, and see if that's the same thing as when I compare 10 over 8. Now the good news is you could reduce all of these fractions in your calculator. If you reduce 15 over 12, and you just type that into your calculator, or if you're good at division, you could always do that, you'll notice that's just 1.25. So I'll make this a little bit smaller and I'll write that below. So one of my pieces is 1.25. So that would be saying my scale factor to get from 12 to 15 is 1.25. The problem is when I divide 9 by 6, I get 1.5 or 1.5. And when I divide 10 by 8, I get 1.25 or 1.25 as well. The problem is not all my side lengths are in proportion because I don't have a common scale factor between all three of my sides. So my argument here is that triangle ABC is not similar to triangle DEF, and my reason being is that not all corresponding sides are in proportion. So I would need all three pairs of those to reduce to the same common scale factor to prove those two triangles are in fact similar. For number 6, a flagpole, something coming straight out of the ground, casts a shadow that's 24 meters long. So if it's coming straight out of the ground, let's say the shadow's on the ground, right? If you look at a shadow, it's on the ground behind you. You know, the sun's over here or something. And Andre, who is standing near the flagpole, let's say he's right there, casts a shadow that's 3 meters long. If Andre is 2 meters tall, so from the ground to the top of his head is 2 meters, then how tall is the flagpole? So if I got a flag right here, I want to know how tall this is. Well, I can assume that, these are both right angles, and that I actually have triangles here that I could set up proportions with. Because the sun should be hitting down on these two people at the same angle. So I'm going to again assume these triangles are similar. I'm going to set up a proportion where I start with the big side. I'm going to start with x. That would correspond with Andre's height over there, 2, is equal to, again, I'm going to go back to my big triangle, 24, over the length of Andre's shadow, 3. And again, remember to solve the proportion, I'm just going to cross multiply. 3 times x is 3x, and 2 times 24 is 48. If I divide out that 3 on both sides, I find that x is equal to 16 meters. So this flagpole is 16 meters tall. For number 7, in the accompanying diagram, triangle ABC is similar to triangle DEF. Some of these labels I need to change just a little bit, so let's see. If DE equals 10, DF equals 16, AB equals x minus 3, and AC equals x, determine algebraically the value for x. Looks to me like I'm going to set up another proportion here, but let me just label my sides. X minus 3 is AB, AC is x, DE is 10, and DF is 16. All right, so x minus 3 over the corresponding side, which is 10, is equal to x over my corresponding side, 16. So again, it looks like I'm going to have to distribute here, so just be careful when you're solving your proportion. I always like to write out the step before the distribution to remind me to multiply that 16 into both my x and my minus 3. So I get 16x minus 48 is equal to 10x. And if I subtract 16x on both sides, remember your goal is to get all of your x's on one side of the equal sign. 16x minus 16x reduces to 0. I'm going to keep writing over here. I have negative 48 on one side of the equal sign, and 10 minus 16, if I subtract those coefficients, is just negative 6. Now that negative 6 is linked to my x with multiplication. So to undo the multiplication, I'm going to divide by 6 on both sides of the equal sign. So my final value is x equals 8, because remember, a negative divided by a negative should be positive. A triangle has side lengths 3, 4, and 5. A second triangle is similar to it. The sides of the second triangle could not be. So I'm looking for not a constant scale factor. Right, so if I'm looking through these, My side lengths are 3, 4, and 5. If I take all of those, and I let the scale factor be equal to 2, my side lengths would be double, so I'd have 6, 8, and 10. So I know 1 could be some possible side lengths for that triangle. Instead, if I half all those sides, I would end up with 1.5 as one length, half of 4 is 2, and half of 5 is 2.5. So if my scale factor was 1/2, that would be consistent. And I'm not really sure for 3. So what I'm going to do is I'm going to divide to see what I get. I'm going to take 6.3, the smallest side there, divide it by the smallest side length of my original triangle. When I do that, I end up getting 2.1. Let me see if that's constant between all of my side lengths. All right, so I'm going to take my middle side, 4, and divide that into my new middle side, 8.4. Oh, I get 2.1 again. Very interesting. And if I take 10.5, my biggest side of the new triangle, divided by the biggest side of my original triangle, again I get 2.1. So all 3 of those pairs of sides would be in proportion. That would just mean that your scale factor is 2.1. You could still figure it out by dividing your side lengths. The problem with number 4, where this falls apart, I'll erase some work here just so we can talk about it, is that if I compare, like let's say 7 to 3, my 2 smallest sides, and I compare that to any of my side lengths, I'm going to pick my middle side length, which is 8, divided by 4. If I'm checking to see if that proportion is 2, when I cross multiply, 4 times 7 is 28, and 3 times 8 is, 24. So those side lengths are not in proportion. And you could do that with the 9 as well to see that none of them really are here. Number 9. The line y equals 2x minus 4 is dilated by a scale factor of 3/2 centered at the origin. Which equation represents the image of the line after the dilation? Remember, if I dilate a line, so this has a slope of 2 and a y-intercept of -4, so this is just a sketch. If I dilate it by a scale factor of 3/2 from the origin 0, 0, it's going to take that distance right there and push it to make it a little bit further down from the origin. So the first thing I notice is that answer choice 3 and answer choice 4 have different slopes, but if I dilate a line, it should stay parallel to it. And remember, parallel lines have the same slope. So what's going to happen here is I end up getting a y-intercept of -6. And all I need to do there is just take the y-intercept of my original line and multiply it by 3/2. So 3/2 of -4 is just -6. So I push it a little bit further away from the origin there. Number 10. The side lengths of a triangle have lengths 8, 12, and 16. If the longest side of a similar triangle has length 28, determine the perimeter of that triangle. So I'm going to sketch a picture here, right? It doesn't have to be drawn to scale. It doesn't need to be perfect. But the idea is I start with some triangle here. I have a similar triangle, which means all the angles are the same and the sides are in proportion. And the longest side is 28. So notice the longest side of your original triangle is 16. So I'm going to put the longest side of my new triangle on the bottom here. So the question is, what had to be my scale factor to get from 16 to 28? So you could set up a couple proportions here if you want to. I'm just going to find my scale factor k by taking my new side, 28, and dividing it by the corresponding old side, 16. When I do that in my calculator, I find that that reduces to 1.75. So I must have multiplied by 1 3/4, or 1.75, to get from my old triangle, my smaller triangle, to my bigger triangle. So to get my new side lengths, I'm just going to multiply each of my original sides by my scale factor. So 8 times 1.75 is 14, and 12 times 1.75 is 21. So remember, to find the perimeter, you just add up all the sides. So I'm going to add 14 plus 21 plus 28, and I find my new perimeter is 63. Number 11. Given WV is parallel to UX, prove triangle WTV is similar to triangle UTX. Alright, I'm going to start my statement reason proof. My first statement is just going to be restating my givens, and I want to think about why they gave me those givens. If I'm talking about parallel lines, I'm either looking for congruent corresponding angles or congruent alternate interior. So I don't see any z's here, but I notice if I translate that angle up, it would land right on top of that angle right there. So I've got one pair of corresponding angles there. So I'll say that angle TUX is congruent to angle TWV. My reason being is that parallel lines form congruent corresponding angles. Again, I'm using some shorthand here. You should write out as much as you can. Again, you might notice that I actually have another pair of corresponding angles on the other side. So if I wanted to lump down here that angle TVW is congruent to angle TXU for the same reason, I could do that, and this would be a three-step proof. But just to show you the other way to do it, I'm going to pretend I don't see those. However, I do notice that if I redraw these triangles, triangle WVT, and the larger triangle, triangle UXT, notice that they both have angle T in them because they overlap at angle T and they share that angle. So an angle that I know is congruent to itself is angle T. So I could also say that angle T is congruent to angle T by the reflexive property, and then I would have my two angles. And that's enough information to state two congruent angles, to state that my triangles are similar. So triangle WTV is similar to triangle UTX. The reason being is just I have two pairs of corresponding angles that are congruent. Again, you didn't even need this step right here for the reflexive property if you saw the other pair of corresponding angles down there. Number 12. In the diagram shown, AB is perpendicular to AC, and D is located on BC such that AD is perpendicular to BC. If ABD is equal to 25 degrees, find the following measures of the angles. Right, well, this angle right here, ABD up here, is 25 degrees. And remember that perpendicular lines form 90-degree angles. So if you have a 90-degree angle on that side of D, this should also be 90 degrees right there. I'm just going to do a little backwards work without looking at what they're asking, just to fill in some angles already. Notice for triangle bad right there, I already have two angles. I have 25 and 90. So if I wanted to find the missing angle, I could just subtract the sum of those from 180 degrees. Because remember, all the angles in a triangle should sum to 180 degrees. So that angle right there is 65 degrees. Now let's do some more detective work. Wait a minute. Angle A is also 90 degrees altogether. So angle BAD plus angle DAC should be 90 degrees. So if I take 90 and subtract away 65, I find that my missing piece down there is 25 degrees. But again, if I look just at the little triangle down here, DAC, I already have two angles. I know I have 90 degrees at D, I've got 25 degrees down there, and again, if I make a quick subtraction from 180, I can find that that angle at C is 65 degrees. So notice there's really only three different angle measures here: 25 degrees, 65 degrees, or 90 degrees. So all three of these triangles end up being similar. So the measure of angle BCA, down in the corner right there, is 65 degrees. The measure of angle CAD, that little one right there, is 25 degrees. And the measure of angle BAD, the one we started with, is 65 degrees. So let's try to prove that I've got two similar triangles with BAC and BDA. I'm going to erase my markings here just to make it easier to look at and say to myself, I want to prove these two triangles congruent. I want to prove triangle BAC, so the full triangle, and triangle BDA, the triangle on top there. So let's get started. I'm going to give myself a statement column and a reason column, and I'm going to restate my givens. They actually gave me a lot in the givens. They told me that segment AB was perpendicular to segment AC, and that segment AD was perpendicular to segment BC. Remember, perpendicular lines form congruent right angles. So I'm going to try to use that to state some congruent angles here. I could say that angle BAC right there, remember that's part of my big triangle, BAC right there, is congruent to an angle in that triangle, BAC. I've got a right angle right there as well. So I'm going to label those two angles. So I'll say that angle BAC, right down there, is congruent to angle BDA. That would be that angle right there in the smaller blue triangle. My reason being is that that was part of the given information, and I know that perpendicular lines form congruent right angles. All right, I've already got one angle. I just need one more. So this might be a little bit hard to see because of the way these triangles are labeled. So I'm going to separate these. I'm actually going to redraw that blue triangle over here, and it might be more obvious. I've got B up there, D is my right angle, and A's over here, and then my largest triangle, which is just a little bit bigger than that, is triangle BAC. Now you should notice both of them have A, but this vertex for A and that vertex for A don't represent the same angle. Because in my blue triangle, A is just part of that right angle right there. However, notice that these two triangles overlap at B, where they share that same angle B. So again, I could use a reflexive property, say that angle B is congruent to angle B here, by the reflexive property. And therefore, I have my two angles. So I could say triangle BAC is similar to triangle BDA, and my reason is always, for right now, for these similarity proofs, is going to be angle-angle. Now for part C, they give me a little bit more information there, so I'm going to redraw these triangles one more time just so I can do some algebra with them. They don't need to be drawn to scale, so that's my bigger triangle. That's my slightly smaller triangle. And they tell me that BC equals 16, BD equals 9, and they say find the length of BA. So you might be thinking to yourself, wait, they must not have given me enough information here. But if you notice, there's BA in that triangle. All right, so I'll label him X. But wait a minute, BA is also in that triangle. And BA is the same as BA. If I look at my picture, that's actually a side length that both of my triangles share. One happens to be the hypotenuse of one right triangle, one is just a leg of the other. I'm still going to set up a proportion. I'm going to start with BA over there, that's X, over the corresponding side, which is 9, is equal to, back to my big triangle, 16 corresponds to X. Again, I'm going to cross multiply. X times X is just X squared. 16 times 9 is 144. So this is asking what number squared gets me 144. If you're not sure, you could always take a square root to undo that squared on the left-hand side of the equation. And the square root of 144 is 12. So my missing side length here in both those triangles, BA, is 12. For the last one, number 13. Given trapezoid ABCD, okay, so that's, maybe I'm going to need to remember some quadrilateral properties here. With diagonals AC and BD intersecting at E, prove triangle BCD EC up there is similar to triangle AED down there. So those are the two triangles I'm looking at. All right. I don't really have a lot in my givens, right? I have that there are diagonals there that intersect. But the important one is that ABCD is a trapezoid. So I have trapezoid ABCD. And I want to think about what was the definition of a trapezoid. Oh yeah, there's at least one pair of parallel sides. And based off of this picture, it looks like BC is parallel to AD. Maybe that'll help me here. So I'm going to state that my side lengths BC and AD are parallel. Now the reason I know that, there's lots of different ways you could word this. I just like to write the definition of a trapezoid. A trapezoid has at least one pair of parallel sides. Right, so it looks to me like BC and AD are ones that are parallel there. And if I have parallel lines, all of a sudden I could start looking for, oh, I've got congruent alternate interior angles there and there, and there and there. So we've done a lot of labeling of angles, and I'm getting kind of tired of it. So I'm going to label that angle up there as 1 by B. That angle down there is 2. I'm going to say that angle 1 is congruent to angle 2. And you could always do this for any proof. And I'm going to say that angle BCE, I'm going to call that angle 3 to help me out. And angle 4 down there, that those are congruent because I know my sides are parallel. And remember that parallel lines form congruent alternate interior angles. Again, I'm using shorthand here. You should write it out fully when you're writing a proof. Well, look at that. I already have two angles. That's enough to say the triangle BEC is similar to triangle AED, simply by angle. Now, for these similarity proofs, usually there's a lot of different ways to do it. I saw the alternate interior angles there, but if you happen to notice those vertical angles first and use those, and only used one pair of alternate interior angles, that's fine too, as long as you could find two pairs of congruent corresponding angles.